Good day, everyone. Let me begin with a curious thought. Have you noticed that whenever you drive a car or switch on a fan, the machine gets warmer? Where does that heat come from? That's the essence of what we call energy degradation. Energy can never be destroyed, but in every transformation, part of it slips away into forms we can no longer use. For instance, in a car engine, a big chunk of fuel energy never becomes motion, it just leaks out as heat into the surroundings. This gradual loss of usefulness is what physicists describe as energy degradation. Now, let's clear a common confusion. The law of conservation of energy tells us that the total amount of energy in the universe remains constant. Sounds reassuring, right? But here's the catch. While the quantity stays the same, the quality of energy keeps dropping. We call electricity and mechanical work high-grade energy because they can easily be converted into other forms. But when this same energy ends up as scattered heat, it becomes low-grade, far less useful. In equation form, delta E total equals 0, but useful energy decreases and heat energy increases. So, conservation ensures the amount, but degradation reduces the usefulness. Let's ground this idea in everyday life. In a car engine, fuel's chemical energy partly pushes the pistons, but most of it is lost as exhaust heat. In an electric bulb, only about 5% produces light, while the rest escapes as warmth. Even the human body isn't efficient. From all the food energy we eat, a major portion just leaves us as heat. And in power plants, vast amounts of generated energy are wasted in cooling towers. If you could see a diagram, you'd find arrows showing energy flowing out as heat at every stage. That's energy degradation in action. Now let's bring in the second law of thermodynamics. It tells us that in every real process, entropy or disorder increases. In simple words, heat will always flow from hot to cold, never the other way round. That means once high-grade energy has become random, low-grade heat, it can't be fully recovered. The entropy equation reads delta S greater than 0 for every irreversible process. And since almost everything around us is irreversible, degradation is simply unavoidable. Here's where efficiency comes in. Efficiency is the ratio of useful work to total energy input. Mathematically, efficiency equals work useful divided by energy input multiplied by 100%. Because of degradation, efficiency can never touch 100%. Even the ideal Carnot engine, which is our theoretical gold standard, is limited by the temperatures of its hot and cold reservoirs. Engineers work hard to minimize losses, but the second law makes it clear some energy will always degrade. Let's test this with an example. Suppose a heat engine receives heat input Q1 of 2000 joules and rejects Q2 1200 joules. Step 1. Apply the efficiency law. Efficiency equals open bracket Q1 minus Q2 close bracket divided by Q1. Substituting values, efficiency equals open bracket 2000 minus 1200 close bracket over 2000. That gives 0.4 or 40%. Step 2. What about degraded energy? Well, the rejected heat, Q2, equals 1200 joules. That's the energy irreversibly lost to the surroundings. So, only 40% becomes useful work while 60% is degraded. A stark reminder that even powerful machines spend more energy in waste than in actual work. So let's wrap this up. Energy degradation doesn't mean energy disappears, it simply becomes less usable. The second law of thermodynamics and entropy growth guarantee that all processes lead to some loss in quality. From engines and power plants to light bulbs and even our own bodies, Energy degradation explains why no device can ever be perfectly efficient. It also tells us why perpetual motion machines are a fantasy. I hope this session helped you see why the real challenge of physics and engineering is not in creating energy, but in using it wisely. Until next time, keep observing how every motion around you hides a story of energy's inevitable degradation.